Hi, greetings from Argentina, buenos tardes. So, again, let's talk about irreducible polynomials over p fields, finite fields of prime number of elements, for just a second. So, remember last time we proved that 1 over n of them is irreducible, where n denotes the degree, and n is large. And on the other hand, n minus 1 over n is square free. It's not divisible by the square of a polynomial. So note that the sum of these two numbers is 1. So if you ever go to Vegas and they offer you a game that they choose a polynomial of a large degree over a finite field at random, of prime order field at random, and you win if it has at least one of these two properties, then it's a fair game because the expected value of points you get there is 1. So you should play this game if they pay you at least evenly. So today we will prove some other things about irreducible polynomials and polynomials over finite fields in general. However, for that we need what I promised before, namely the unlabeled version of the exa-log schema. So remember, it started with a definition on when did we say that a function gz is of k lambda logarithmic type, and there were three conditions. The first one was that there's a unique singularity on the circle z equals rho, and that was at rho itself. Then gz was continuable to a delta domain, and there was a third condition which I just write up the main terms for, is that gz was logarithmic in the sense that it was equal to a constant time a kappa times log of 1 over 1 minus z over rho plus another constant lambda plus smaller terms. Okay, this was the condition, and this will not change for the unlabeled version of the scheme. So when this happens, then we say that the function gz is kappa lambda logarithmic. Okay, kappa lambda logarithmic. Now there is a change in the second definition, namely the definition of what construction we are considering for the exa-log schema. So recall that for labeled structures, it was, or it should be 1 hour since we're in the United States, or anyway you are. For labeled structures, it was that F was the set of G, a bunch of G structures. But for unlabeled, that doesn't make sense because our atoms are unlabeled, so I can't talk about their sets because there will be repetitions. Hence, what we consider here is that F is now a multi-set of G. Okay? So, furthermore, we also require in this case that omega is less than 1. Sorry, rho is less than 1. So the convergence radius of G is less than 1. Okay, so if this happens, if F is a multi-set construction whose elements are the constructions of the G type, and rho is less than 1, then we talk about an unlabeled exa-log schema. So F and G form an unlabeled exa-log schema. So now that I discussed how the conditions are somewhat different for the unlabeled version of the schema, let me talk about what the theorem says differently. So remember, the theorem for the labeled case had three statements: one about the growth rate of the coefficients of gz, one for the coefficients of fz, and one for the average number of g components in a random f object. So the good news is that there is no change for gz. It's still the same rule as we learned from the labeled subjects, which is not very difficult. Kappa over n over rho to the negative n times 1 plus something smaller log square n. Oops. But that's the easy part. Now for the others, there is a difference which is easy to encode, but it's somewhat harder to actually do computations with. So let's look at them one by one. So the result for f is different from the labeled case. So we get that the coefficient of z to the n in f, the multi-set structure, is asymptotically equal to e to the lambda plus r0. This r0 is the difference. This is what was not there for the labeled case, divided by gamma value at kappa, the gamma function's value at kappa, times n to the kappa minus 1 times rho to the negative n plus smaller terms. Okay, so this r0 is the different. That's the different part. That's the difference from the labeled case. Okay, so this is that r0, which is a constant, but I will tell you in a second what constant it is. That's the difference. And finally, I have to say, what do we know about the average number of components in a random F structure of size n? And again, the result is similar to what it was in the labeled case, but it's slightly different due to some constants. So the answer is that it's kappa, the average number of components is kappa times log n minus phi k. Remember, that's what I was talking about last time, that phi k, psi k, psi kappa has a typo in the book, plus lambda, that's still the parameter from the exa-log schema, plus r1 plus smaller terms. And r1 is a constant, just like r0 was, and it's somewhat similarly defined. Namely, r1 is again the sum of j goes from 2 of g rho to the j. There is no division by j this time. And note that in the unlabeled case we required rho to be less than 1. So these rho to the j's are always less than 1 as well, and then you could prove that these sums are always finite. We do not prove the unlabeled version, just as we didn't prove the labeled version as well, but the proofs are not difficult. The only difficulty is just to understand all the notation and all the things that we are dealing with. The steps themselves are not that difficult. So anyway, time for applications. Again, remember that we are doing a study of polynomials over the finite field fp, where p is a prime number, and we will, over the variable z, not x, over the variable z. Okay, and remember that we looked at them as sequences. We look at monic polynomials. Let p actually be not all polynomials, just monic polynomials. So their leading coefficient is 1. And then we identified them with their sequence of coefficients except the leading coefficient. Right? Where A is the set of elements of the finite field, so it consists of 0, 1, all the way to Pn minus 1. So remember that, I mean, this is trivial. From that it follows that the generating function of all polynomials is of course 1 over 1 minus p times z. What's not trivial, but what we proved last time, is that we have a generating function for the irreducible polynomials. Remember the number of irreducible polynomials over this field. We proved that with the Möbius inversion formula after using the multi-set generating function. And we got that it's equal to log of 1 over 1 minus z plus a Möbius inversion formula sum. The sum as k goes from 2 of nu k over k times ln of 1 over 1 minus p times z to the k. I mean, what we proved is equivalent to this. We just separated the first term here because it was so nice, right? It's ln of 1 minus z to the first times 1 over 1. So if you look at the formula that I just wrote up for iz, from that it follows that there is a logarithmic, an x-log schema for iz itself, because it is of the form log of 1 over 1 minus z plus something. So because of that log of 1 over 1 minus z, we see that kappa is equal to 1. R was an infinite sum. Remember, it was the sum of nu k over k times log of 1 over 1 minus p z to the k. So if you think about it, this will be convergent with convergence radius z over 1 minus p. So z is equal to 1 over p. And that it's not that hard to prove. And then you can take lambda to be the value of this sum r at 1 over p. So the x-log schema conditions are satisfied with the irreducible polynomials being g and all polynomials being f. Hence we can apply the third part of the theorem, that the average number of components is kappa times log n, which in this case is equal to 1 times log n, so just log n. So the average polynomial of degree n over fp has log n factors. It can also be proved that the variance is also log n, so the standard deviation is square root of log n, which is very small compared to log n. So the distribution is concentrated around its mean. In other words, it's extremely likely that a big polynomial of degree n has very close to log n factors. And now comes the punchline application. At least I enjoyed it a lot. How many divisors does a polynomial of degree n over fp have? How many divisors does it have? Not just irreducible divisors or factors, we have already done that, but how many divisors altogether? Okay, this is similar to how you find how many divisors an integer have, right? You take the prime factorization and you go from there. So let's say that you have a polynomial and it can be written as, say, t1 to the e1, t2 to the e2, blah blah blah, tk to the ek, where the ti are irreducible polynomials. Right, over finite field it doesn't necessarily mean that they are of first degree, but they are irreducible. And let's say everybody is monic again, everybody has first coefficient 1. Okay, then clearly the number of the number of divisors of this polynomial w will be e1 plus 1 times e2 plus 1 blah 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 ek plus 1, right? Because each of these factors can be taken 0 times or 1 times or 2 times or ei times. The question is what the average of all this is. And so here is something surprising. The book says, without much explanation, that the average is the coefficient of Zn in pi, j goes from at least 1, but this is the big trick here, what that really means, times 1 plus 2z to the j plus 3z to the 2j and so on. And again, this is an infinite product of these infinite sums divided by the coefficient of z to the n in the somewhat simpler but very similar infinite product of infinite sums, which is just 1 plus z to the j plus 2 times z to the, so not that's the point, there's no 2 times, just z to the j, z to the 2j, and then z to the 3j and so on. Okay, so this is just like as you see in the generating function of partitions. So it's 1 plus z to the j plus z to the 2j plus z to the 3j and so on. And then the book really surprised me by writing that these somewhat complicated expressions were equal to the super simple expression z to the n pz square over z to the n in pz. And remember that pz is the super simple generating function 1 over 1 minus pz. Okay, and so therefore this is how it will start for the two polynomials of irreducible polynomials of degree 1. We will have this times this, and for the one irreducible polynomial of degree 2 we will have this, and you multiply it out and you see that indeed that starts as 1 plus 2z plus 4z squared, so it indeed ends up by being 1 over 1 minus 2z, and in general it will work because simply every polynomial of degree n over any field is put together in a unique way, right? Unique factorization theorem from irreducible polynomials. So what I didn't understand is, for instance, in the denominator where we have that pi 1 over 1 minus z to the I, or j, whatever, where j goes from 1. How come it's not just the generating function of partitions? How could that possibly be equal to 1 over 1 minus pz? And the solution is that it's very misleading to put j larger than or equal to 1, because that somehow suggests that there will be one factor for j equals 1, one factor for j equals 2, one factor for j equals 3, and so on. But that's not the case. There will be one factor for each irreducible polynomial of that degree, so there will be more than one for some j's. Let's see an example. When n is 1, or j is 1, sorry, then there are the irreducible polynomials p, let's say we are over the two element field, and p and p plus 1 are both irreducible polynomials of degree 1 over z2. So there will be two polynomials corresponding to j equals 1. However, for j equals 2 there will be only one, because there's only one irreducible polynomial of degree 2, because that is p squared plus p plus 1. The others are not irreducible because, well, p squared plus p is of course p times p plus 1, and on the other hand p squared plus 1 is equal to p plus 1 squared, since we are modulo 2. And with this, now with this correct interpretation of the indices j, now the book's formula makes perfect sense. So indeed the average number of divisors is the total number of divisors divided by all polynomials, right? And so it's indeed this divided by this. Think about the numerator, but it's not difficult because it just shows that if something shows up 10 times, then in a divisor its exponent can be anywhere between 0 and 11. On the other hand, these are super simple power series, right? And the ratio of these coefficients is always n plus 1, right? We know that the coefficients of 1 over 1 minus 2z squared, 1 over 1 minus 2z squared like that are n plus 1 times 2 to the n, and if it's p instead of 2, then it's n plus 1 times p to the n. So this is the punchline, that the average number of divisors of a random polynomial of degree n over a finite field is always n plus 1, and that doesn't even depend on p. So I find this and the proof completely remarkable. See you next time.